Okay, let's unpack this. Sorting information. It's one of those fundamental challenges in computer science, right? Something we bump into all the time.
Absolutely. Files, data, you name it. And there's just so many ways to actually do the sorting.
Yeah, tons of algorithms, each kind of good for different things. Today, we're diving deep into one known for being pretty efficient, especially with memory, Heap Sort.
And we're using the Hello Algo resource you brought, specifically their section on Heap Sort. It lays things out really clearly.
Exactly. So our mission here is to really get Heap Sort. Like, understand how it works step by step, see the clever way it uses that heap structure, and, lock in those key performance facts.
Yeah, we want you to walk away feeling like you truly grasp it so it sticks, like building a solid mental picture of the whole process.
So let's dive right in. Fundamentally, what is Heap Sort? What's the big idea?
Well, at its heart, Heap Sort is an efficient sorting algorithm, comparison-based. But the key thing is it's completely built on the heap data structure.
Ah, okay. So you can't really get Heap Sort without getting heaps first.
Pretty much. Understanding how to, build a heap, add things, and especially how to pull elements out, extraction, that's crucial.
Yeah.
The source even flags that, saying, make sure you've covered heaps before jumping in here.
Makes total sense. It's not standalone, it's heap-based. It takes those heap mechanics and, well, applies them to sorting an array.
Exact.
Now, the material you shared mentions a sort of simpler, more basic way you could use a heap for sorting, but it's not how we usually do it, because it has a downside.
Right, there's a conceptually simpler approach first. You take your array, the input, and you build a min heap from it.
Min heap. So the smallest element is always right at the top, the root.
Precisely. Always accessible. So with that smallest element ready, you could just, repeatedly extract it, pop the smallest off the heap.
Okay.
And as you pull each smallest element out, you'd stick it into a new array, sequentially.
Ah, I see. So you pull smallest, next smallest, and they naturally line up in sorted order in the new array.
Exactly. Build min heap, pop smallest repeatedly, put in new list. Seems straightforward.
Yeah, sounds simple. So what's the catch? Why don't we usually do it that way?
The big drawback, as the material notes, is that you need that additional array.
Hmm.
And if your input array is massive, well, you need another massive array just to store the results. That's pretty space-consuming.
Right, double the memory. And if you're dealing with huge data sets, memory usage, the space complexity, that can be a really big constraint.
Totally. And that's why the standard heap sort, the more elegant version, works differently.
Okay, it avoids that extra space.
Exactly. The implementation everyone uses is much smarter because it sorts in place. Minimal extra memory working right inside the original array.
Okay, let's get into that elegant in-place method then. It's got a few key steps. How does this version kick off?
This version, the standard one, starts by taking the input array and turning it into a max heap.
Max heap. Okay, so opposite of the simple idea. Now the largest element is at the root. Index 0.
Correct. Largest element is right at the top.
Got it. Build the max heap first. And the material notes this initial build step takes, what, ohinin? Time. Which seems pretty fast for setting things up.
Yeah, building the heap itself is surprisingly efficient, just ON. So once you have that max heap with the biggest element sitting right there at index 0, you start the main sorting loop.
Right. And step 2 is the swap, isn't it? Swap the top element with the heap's bottom element.
Yes, you swap that largest element at the root, index 0, with whatever element is currently at the very end of the part of the array we still consider the heap.
And then comes the clever bit. You reduce the heap's length by 1.
This is where the in-place magic happens. You've just taken the biggest element from the unsorted part and put it exactly where it belongs in the final sorted array at the very end.
Ah, okay.
By mentally shrinking the heap size by 1, you're basically saying, okay, that last spot is now sorted. Let's ignore it. The active heap is now everything before that.
So the sorted section grows from the right end of the array, and the heap part shrinks from that same end.
Precisely. But wait, after you do that swap, the element that just landed at the root, the one that was at the bottom, is probably not the largest anymore, right? It could be small.
Yeah, it likely messes up the max heap property for the remaining smaller heap.
Exactly. And that brings us straight to step 3, fixing the heap.
Restoring the max heap property, how do we do that?
You run the sift down operation, starting right from the new root at index 0.
Sift down. Okay, that's the core heap fixing mechanism. You look at the root, compare it to its kids, and if it's smaller than the bigger kid, you swap them.
Right, and you keep doing that, pushing the smaller element down the tree, swapping with the larger child each time until it's either bigger than its children or it hits the bottom, becoming a leaf.
And this effectively bubbles the new largest element in that remaining section back up towards the root of the shrinking heap.
Exactly. And, crucially, as the source mentions, that sift-down function needs to know how big the current heap is. You need to pass in that shrinking length parameter so it knows where the heap actually ends now.
Makes sense. You can't sift down into the already sorted part.
Right, so sift down makes sure that after we've moved the biggest element out of the way, the next biggest element in the remaining heap gets back to the root, ready for the next swap.
Okay, so step 2, swap, and step 3, sift down, are basically one cycle. Find the max, put it at the end, fix the heap.
That's the core loop. And step 4 is just repeat.
Repeat steps 2 and 3. How many times?
You do it n1 times, where n is the total number of elements.
N1 rounds. Why not n times? Why stop one short?
Good question. Because think about it. After you've done this n1 times, you've successfully placed the n1 largest elements into their correct final spots at the end of the array.
Okay.
So what's left? Only one element sitting at the very beginning, index 0. And since all the others are larger and correctly placed after it, that one remaining element must be the smallest one.
And it's already in the correct first position. No need to do anything with it.
Exactly. The array is fully sorted after n1 rounds.
That repeated swap and sift down. It really is like that extraction idea from the simple method, but cleverly adapted to work without extra space.
It's the same core logic, yeah. Find the max, which is at the root, extract it by swapping it to the end, and then fix the remaining heap structure, all within the same array. The code examples show this really well, how sift down gets called inside the main cert loop with that decreasing size.
That breakdown really helps visualize it. Build the max heap once, then loop, swap root to end, shrink heap view, sift down the new root. Okay, so let's talk performance, the bottom line characteristics. Time complexity first.
Heap sort is consistently O(n) log n, time complexity.
O(n) log n. Okay, and we can sort of see where that comes from, right? Building the heap initially is O(m).
Yep, O(n) for the build.
Then we loop n1 times. Inside the loop, we do a swap, which is quick, O(n), and a sift down. How long does sift down take?
Sift down on a heap of size, say, AK takes O log k time, because you're basically just traveling down the height of the heap, which is logarithmic.
Right. And since our heap size k goes from roughly n down towards 1, each sift down is at most O log n.
Exactly. So you have O(n) for the initial build plus about n operations that each take O log n. Add those up, the n log n term dominates. So O(n) log n overall.
Got it. And the source mentions it's non-adaptive. What does that mean again?
It means the algorithm's performance doesn't really change much based on how sorted the input array already is. Whether it's random, reversed, or almost sorted, heap sort takes roughly the same O(n) log n time. It just does its thing regardless.
Okay. Consistent, if not faster on easy cases. Now, memory. Space complexity. This was the big advantage over the simple idea.
Yes. This is a huge plus for heap sort. Its space complexity is O(1).
Constant space. That's amazing. And confirms it's truly in place.
Absolutely. All the sorting, the swaps, the sifting down, it happens right there within the original array's footprint. You only need a tiny constant amount of extra space for maybe a temporary variable for the swap or loop counters, nothing that grows with the input size n.
That O(1) space is really powerful, especially, like you said, for enormous data sets where you just can't afford to allocate another huge chunk of memory.
Definitely a key selling point in memory-constrained situations.
All right, one last characteristic. Stability. Does heap sort keep elements with equal values in their original relative order?
No, it doesn't. Heap sort is non-stable.
Non-stable. Okay, why not? Where does the order get messed up?
It's that swap again. Step 2, swapping the root, the current max, with the element at the very end of the active heap. If you happen to have two equal elements, say 2 5s, one might be the root at some point and get swapped way down to the end of the current heap. The other 5 might still be somewhere else. When the dust settles, there's no guarantee they'll end up in the same relative order they started in. That swap disrupts the original order.
So that crucial swap that enables the in-place sorting is also what sacrifices the stability, a trade-off.
Exactly. You gain O(1) space, but you lose stability.
Okay, I think we've really dug into heap sort now. We started by understanding it's heap-based. We saw the elegant in-place process, build that max heap up front, then loop n1 times doing the swap root to end, shrink the view, and sift down the new root dance.
And we've nailed down its key stats, that reliable O(n) log n time, the fantastic O1 space complexity because it's in place, and the fact that it's non-stable due to those swaps.
It really is a clever piece of algorithm design, using the properties of a heap so effectively to sort right inside the original array. Super memory efficient.
Yeah, it's a great example of how knowing your data structures really opens up possibilities for efficient algorithms.
So let's leave you with something to think about. You've got all these sorting algorithms in your toolkit now, including Heap Sort after this deep dive. Picture this. You're faced with sorting a truly massive data set, gigabytes maybe, but your system has very limited extra RAM available. How does knowing Heap Sort's specific profile O(n) log n time, that critical O1 space, but also its non-stable nature, help you weigh it against other sorting methods? When would that specific combination of traits make Heap Sort the absolute right choice for the job? Definitely something worth considering next time you need to sort.